Welcome everyone to Iris Biotech's 9th online workshop. True to our slogan, Empowering Peptide Innovation, we are keen on knowledge exchange and getting in contact with scientists all over the world. Therefore, we started this workshop series in summer 2021. Today, our focus is once more on click chemistry, and in particular on recent innovations in the field. Our guest speaker, Professor Rob Liskamp, will present a fascinating journey from copper-assisted to TMT HSI click chemistry. My name is Raimund Meyer. I'm working as COO at Iris Biotech, and today I will guide you through this online workshop. If you wish to announce your participation on social media, please feel free to use the hashtag Iris Workshop Series, which is also displayed right now, hopefully in the Microsoft Teams chat. To have a pleasant experience for all participants, as always, I would like to begin with some technical guidelines. To ensure the best possible audio and video quality, all participants are automatically muted and your video camera is switched off. This live event is recorded. Thus, if you enter late or miss anything, please check on the bottom left side of your Teams screen if you are watching the recording or if you are live, which is shown by the red broadcasting symbol. You have the possibility to pause the video, rewind, or jump back to the live session. In addition, the recording of the workshop will be uploaded on our homepage afterwards. Questions can be submitted by using the Q&A chat of Microsoft Teams. You can enter your name or submit your questions anonymously. We will frequently check the questions, publish them, and submit them to the respective speaker. If you have any technical queries, you can also submit them in this Q&A chat. Our technical assistant will then connect with you and try to solve the problem. Initially, the questions are just visible for the organizers and will then be published to the audience. So don't worry if your submitted question does not appear on the chat screen immediately. I would now like to quickly give you an overview on today's agenda. We will start with a short company and topic introduction by our project manager Karin Rustler, and afterwards our external speaker, Professor Rob Liskamp, will present to you his research on fast copper-free quick reactions. As mentioned, questions will be collected throughout all talks in the Q&A chat and are forwarded to the speakers. Of course, you can also get in contact via email or phone call after the workshop. One last note from my side, if you accidentally close your Microsoft Teams window, don't panic. As the workshop is also available as recording, you won't miss anything. Just relog in and view the recording. You can then also play this recording at increased speed until you catch up with the live event again. So after this technical intro, let's continue with the first agenda point, a short introduction to our company by our project manager, Karin Rustler. Karin studied biochemistry at the University of Regensburg and obtained her doctoral degree in organic chemistry for the synthesis and characterization of photoswitchable compounds. Beginning of 2020, she joined Iris Biotech as a project manager, and in the meantime, she's now our head of marketing and sales. Karin, thank you for your time. Please go ahead with your presentation.
Thank you, Raimund, for the kind introduction, and also welcome from my side to today's online workshop. Within the next slides, I want to give you a brief introduction to the company Iris Biotech, as well as the topic click chemistry. Iris Biotech has been founded in 2001. In 2013, due to the growing demand for customized products, we started the Iris Biotech laboratories, which are located in Willstedt, so close to the French border, whereas Iris Biotech is located in Marktredwitz, so close to the Czech border. Our portfolio comprises more than 6,000 different products. To realize this, we are working together with around 15 manufacturing partners around the globe, which we select very carefully. Having only qualified partners on board allows us to realize a complaint rate consistently below 0.5%. To give you not only facts and figures, I also want to show you the beautiful landscape we are surrounded by, as well as a picture of our company building in Marktredwitz. We see ourselves as qualified supplier and competent consultant and want to support our customers in the design and execution of their projects, no matter if it's in small research scale or commercial bulk scale. Our portfolio provides building blocks and reagents for peptide synthesis and modification, but also advanced linkers for conjugation, as well as drug delivery technologies, all rounded up by our custom synthesis service. And as you can already see, one part of our portfolio also deals with click chemistry. True to our slogan, empowering peptide innovation, we are keen on providing innovative building blocks. So yeah, let's say just out of the recent publications into our portfolio. We want to make these building blocks available for the whole scientific community and also spread information about their benefits and use cases. And this is also the reason for our workshop series. We want to exchange knowledge between the, let's call them inventors and the users, so the researchers. Today, our topic is innovations in click chemistry. And as Raimund already mentioned, we are pleased to have Professor Rob Liskamp with us. Before we jump into the innovative part, I would like to give you a very brief summary on the topic click chemistry, which was awarded with last year's Nobel Prize. In principle, there are 3 types of click chemistry: the copper-catalyzed azide-alkyne reaction, and then 2 types of copper-free click chemistry: the strain-promoted azide-alkyne cycloaddition, and on the other hand, the inverse electron demand Diels-Alder reaction of tetracenes. In the first type, an azide reacts with an alkyne under formation of a triazole. But the main drawback in this regard is that the presence of cytotoxic copper limits in vivo applications. The second generation is based on the reaction of a strained alkyne, such as DBCO, for example, as you can see on the slide, with an azide. However, also here there is a drawback. These strained alkynes usually show only moderate reaction kinetics and are very bulky and rather hydrophobic. The third type is not, let's say, the usual azide-alkyne reaction, but it is based on the reaction of a tetracene with a strained alkene. In today's workshop, we want to focus a bit more on the second type, so strain promoted between alkyne and azide. And in this regard, Rob is giving insight into the use of the clicker, strained alkyne for copper-free click chemistry, and its advantages. So, Rob, we are already excited to hear more about this topic. With this, I'm already through with my quick introduction. So thank you all for your kind attention. And yeah, excited to hear the main part.
Yeah, thank you, Karin, for giving this introduction. So now let's go on with our highlight and switch to the external guest speaker, Professor Rob Liskamp. Rob, you can already start sharing your presentation now.
I think I've done that.
Okay, fine. So Rob started chemistry originally at the University of Nijmegen and obtained his PhD in bioorganic chemistry in 1982. He then went to America as a postdoctoral fellow at the Institute of Cancer Research of Columbia University in New York. Then returning to Europe, he started as an assistant professor at the University of Leiden and in USA again as a visiting professor at the UCLA, followed by a position as professor of molecular medicinal chemistry at Utrecht University. In 2013, he was appointed professor and chair of chemical biology and medicinal chemistry at the University of Glasgow, while maintaining a guest appointment as professor at University in Utrecht. Nowadays, he's an honorary senior research fellow in the School of Chemistry of the University of Glasgow, guest professor in the Cardiovascular Research Institute of Maastricht, and a consultant of the company Crystal Therapeutics. His research interests include the synthesis of biologically active modified peptides and peptidomimetics, dendrimers, peptide folding, and protein mimics, including synthetic antibodies and vaccines. Rob, it is a great pleasure to host you as our guest speaker. The stage is yours. We are looking forward to hearing about your research. And for the audience, please post your questions by using the Q&A chat.
Thank you very much, Raymond, for this very kind but also lengthy introduction. I'm glad it's not taken from my time. Today, I really want to discuss with you the beauty and versatility of simple click reactions. I want to emphasize that, from copper-1 assistant to TMATH-SI click chemistry. There has been a tremendous amount of activity in the areas of bioconjugation using bioorthogonal reactions, but we feel that the most simple and effective methods will prevail. We see that often in chemistry, simple methods and effective methods will prevail. The outline of my talk is roughly as follows. After a short introduction into the necessity of bioorthogonal, can you still hear me? Yeah?
Sorry for interrupting you. I think we cannot see your presentation yet.
Then we have to go back again because
now they are visible for the audience.
Yeah, and now I go to presentation mode. And now you can see.
That's it. Great.
Everything?
Yeah.
Yeah.
Okay, I'll start over again.
Yeah, perfect. Thank you, Rob.
Okay. Apologies for some technical problems. We always can blame a Mac for this. Today, I wish to tell you about the beauty and versatility of simple click reactions, from copper-assisted to TMATH-SI click chemistry. There has been a tremendous amount of activity in the areas of bioconjugation using bioorthogonal reactions, but we feel that the most simple and effective methods will prevail, which is always the case in chemistry, especially, for instance, if you look at peptide chemistry. A brief outline of my talk is as follows. Briefly, I will mention something about the necessity of bioorthogonal reactions. Then I will move to the Staudinger ligation reaction, and quickly after that to click chemistry, which is actually the copper catalyzed click chemistry. And then we'll move, after some developments of which I want to illustrate with using copper click chemistry, to the problems related to this. And we come out to a very important reagent which has been developed in the past, which is BCN, but still we needed significant improvement. And so we moved on to develop another derivative, which is called TMATH-SI clicker, which is based on TMTH. And this is a very fast reacting, not too hydrophobic click reagent. Of course, I will discuss some derivatives and properties, and we move to application. And then I will end the most of the scientific part of the presentation in the development of two PCA derivatives, which are used for the modification specifically on the N-terminus of native peptides and proteins. And of course, we will have some conclusions there. Now, the necessity of bioorthogonal reaction, they're really necessary for selective modification of biomolecules. If you wish to introduce a functional molecule on a biomolecule, you need to have something which is reacting selectively one part of the molecule and not with the other functional groups. And actually, if you really are very honest, until 2000, the only real bioorthogonal reaction was the reaction of a thiol from a cysteine residue in a peptide or protein with a melamide derivative. And that's understandable because there are not that many cysteines in a peptide or protein, so you will have the possibility of a selective reaction if you expose your peptide or protein to a melamide derivatives, and there are many of them. And so under the right conditions, this cysteine thiol, and you have to have the right conditions, that means pH, it will react with the melamine. If the pH is too high, then even lysines of a peptide and protein will react. And this was really a reaction which has been used for thousands of times. And it really has been a versatile reaction, but has some disadvantages as well. Now, this started to, and I think the disadvantage was clearly realized also by Carlo and Bertozzi. This started to change in 2000 by the breakthrough discovery of the Staudinger ligation reaction, which was based on the reaction of an azide with a phosphine. And this is the old-fashioned Staudinger reaction, which is used for the reduction of an azide to an amine. But this was used very cleverly by Carlo and Bertozzi for the reaction, the coupling reaction of a phosphine-containing molecule with an azide. Now, of course, normally azides are not present in biological systems or biomolecules, but what is possible that they can be introduced, for instance, by the feeding of an feeding of azidote sugars, or if you want to introduce an azide moiety in a peptide or protein, that's feasible nowadays too. And if you have this combination of an azide with the phosphine, really can have a bioorthogonal reaction, the reaction of one type of functional groups in the bioenvironment and not reacting with another, meaning it's orthogonal to any other functional group. But in my view, the real paradigm change, and I just want to mention first that the Staudinger ligation, of course, got a Nobel Prize last year, as Karen already mentioned, but the real change came in my view, with the development of the copper-click reaction independently by Morten Meldal and Barry Sharpless. And it was based on the Huisgen reaction developed in Germany in the 50s by Ralph Huisgen. And this was the reaction of an azide with an alkyne. But they found by copper catalysis and that was really a breakthrough, that the reaction could become very selective, only giving rise to the formation of one isomer. It could be carried out at room temperature, and it was very selective. So it's not surprisingly that this finding, this discovery, was rewarded with the Nobel Prize together with the work of Carlo and Bertozzi to Morten Meldal and Barry Sharpless. Now, in our own work, we found also that this copper-catalyzed azide alkyne cycloaddition reaction is a really versatile reaction for the synthesis of many biomolecular constructs. And they, of course, contain a plethora of functional groups. Now, in the work of Tom Meuleman, for instance, in my former group at the University of Glasgow, he could introduce 3 different cyclic peptides on a scaffold containing alkyne moieties, giving rise in the click reaction to the triazole linkages. And this has been used for the synthesis of hepatitis C virus envelope glycoprotein epitope mimics. Ondra Longren in my group could use this same click reaction, and I want to emphasize again, these are highly functional molecules, and they only react with the azides and the alkyne, and giving rise to these constructs which are protein mimics, and mimics in this case of infliximab or Rimicade, which is clinically used as a biologic for the treatment of human tumor necrosis factor alpha, which plays a role in human autoimmune diseases. it's important to realize that these protein mimics are considerably smaller than the native antibody. So that has some potential for alternative treatment. So we could use it for synthetic vaccine mimics. We can use it for synthetic antibody protein mimics. And another example of that is the mimic of for the synthesis of an HIV discontinuous epitope mimics as a potential synthetic vaccine. I think it's interesting to note that there is still not a vaccine against HIV. So by making a cyclic peptide, carrying out a alkylation reaction, introducing an azide here, one obtains a cyclic peptide which can be clicked onto, in this case, a scaffold containing orthogonally protected alkyne moieties, which means that first you can introduce a cyclic peptide on this position, then on this position, and then on this position, enabling the possibility of making scaffolds with different cyclic peptides. So here you see the huge potential of the copper catalyzed click reaction. Also, the bioorthogonal reaction, I have to mention first that this work was being carried out by Paul Werkhoven and Helmus van der Langheim. Paul worked in my group at Utrecht University, and Helmus worked in my group in Utrecht and in Glasgow. I think they did a very nice job here. Now, also the click reaction was used for the synthesis of much smaller constructs. And in this case, we made mimics of the antibiotic vancomycin. There is a need for new antibiotics, so we're looking at that here. And here, the triazole ring is used as a conformational constraint in order to be able to make a mimic of the cavity of vancomycin. So here we use click chemistry with another meaning. It's really easy to use it, but the triazole moiety has a function here. And the kinase synthesis of kinase inhibitor, the triazole moiety has a connecting unit here. It's just merely a connecting unit, but a unit which can be easily introduced because the reaction is so mild. So we can take a number of pseudo substrates here and kinase inhibitor, and we can connect a number and we can obtain a number of these pseudo substrate ATP inhibitor constructs and finding the right one for of the compound for inhibition of protein kinase C in this case. What is also important that the click reaction can be used in a multivalent system, in the preparation of a multivalent system. Now, of course, you know from organic chemistry, it's already very difficult to react one molecule with another one, but it's even more a bigger challenge to have several moieties and react them with a particular molecule. And that's happening here. Here you see all the triazole moieties which are obtained after reacting of this dendrimeric construct with an azide. Now, to speed up the reaction, of course, we need copper catalysis, but we use microwave chemistry here as well. And then you can come up with multivalent system, and multivalent systems are important because they show a better binding than a monovalent system. And even up to 16 multivalent system containing 16 different 16 ligands can be created. So this is a powerful application of copper click as well, assisted by microwave. But thanks to the very versatile and quick reaction of copper click, this is working. Now, does it mean that it's always working? Now, I'll start with that here, where copper starts to be a problem. And copper starts to be a problem here, where we have this particular molecule. This is octreotide with a chelator. And a chelator has to contain a radioactive isotope. And this radioactive isotope is important for the imaging. And because we can make this particular construct, and here we see multivalency, we see number of ligands which are attached to a scaffold here, and finally we need this chalatum moiety. But this chalatum moiety can also bind copper, meaning this is giving a reduced binding of the radioactive metal ion. So we need something there because we see clearly the disadvantages of copper-assisted click here. Now we found that because we started the development of copper-free click chemistry. Now what kind of copper-free click chemistry did we develop? Now first of all, let's go back again. A chelator may bind copper, so the presence of that binding interferes with the effective radioactive labeling. Also, people think, and it's not exactly proven in this way, that lysine, histidine, and glutamine residues can also bind copper-1. But what is certainly true that copper-2 can lead to oxidation. So, now, and Karen already mentioned that the requirement for catalysis by copper has been an obstacle for application in the biological sciences. Now, there are a couple of remedies, limited amount of copper catalysts, sequestering of copper catalyst, everything has been used for the John exchange, clay, and so on. But you can start changing the azide and alkyne component, and we did some work there, and I want to share with you. But then we moved to also to changing entirely the alkyne component. Now, first we worked on sulfo-click, and we modified the azide and the alkyne. Now, how did we do this? We took a sulfonyl azide, which we cranked up the reactivity of the azide, and we can react it with the thio acid, and this gives rise to a kind of nice click reaction, which is not requiring any copper catalysis. This sulfonyl acyl imide is being formed, and Remco Merckx, he was doing really very nice work in this area, and he could use that for site-specific conjugation. So you have a big molecule with an azide, and it's reacting with the thio acid. Now, chemical ligation, we can connect two big molecules together, sulfonyl azide and a thio acid containing molecule, and we get this construct. Now, this was very fortunate for us, and that's why I want to share it with you. And one of the nice thing of it was that we could easily prepare the sulfonyl azide. Also, it was resistant to many organic chemical conditions. It was easy to prepare the thio acid, and the reactions, the sulfo-click reactions, were very complete. And I just want to show you where it has been very useful. And that was actually with the preparation of this octreotide containing construct, which was used for the imaging of tumors. And we used the sulfo-click reaction as the last reaction for introducing this chalatum moiety. So this was work carried out by Cheng Yim in my group. And so this was in fact very promising for this type of compounds. But of course, as always, there was a kind of a disadvantage of the sulfo-click reaction. And that was still the requirement of the reaction components, especially the thio acid, because the thio acid can be oxidized, and then there's not sufficient present, etc. So that made us realize that we had to move a little bit different. So we went on together with a lot of people to start developing strain-promoted azide alkyne cycloaddition reaction. And that was really a paradigm change. What one does is one takes the same azide, but one increases the reactivity of the alkyne component so that no longer copper catalysis is required. And that was the development of strain-promoted azide alkyne cycloaddition. Now, just let me remind you, this is the thermal azide alkyne cycle addition of Huisken. He heated up the azide together with the alkyne, and you get both components, the 1,4 adduct and the 1,5 adduct. This is, of course, we just want to have one isomer, but you have to heat up. The Nobel Prize finding of Morten Meldal and Barry Sharpless was cranking up the reactivity of the alkyne and making sure that it also could donate the azide to the copper moiety which is on the azide, and it leads to this nice 1,4 adduct. Now, if you want to get rid of the copper 1, the only possibility there existing is making the alkyne very reactive by straining its bond angle. It likes to have a bond angle of which is linear of 180 degrees, but if you can make this angle a lot smaller than 180 degrees, it will react because it wants to relieve its strain, and by forming an alkene, which is sp2 hybridized and can have actually angles. So that's a very important development. Now, the development of strained cycloalkynes. A lot of people worked on that, and on this particular nice slide, which is in the brochure of IRIS, brochure for click chemistry, one sees the tremendous developments here. And one can see that actually a lot of 8-membered rings have been used, mostly 8-membered rings have been used because they give rise to this strain promoted strained alkynes. There's just one 9-membered ring. It's important to realize on this nice graph that the reactivity is logarithmic. So meaning 3 and 2 means actually that there is a 10-fold difference in reactivity. And with the lipophilicity, the same is true. 4 and 5 here, there is a 10-fold difference in lipophilicity. So although it's a nice representation, one has to look at the reactivity. And actually it means that some compounds are very low in reactivity and some are really a lot better. Now, one of the breakthrough reagents, in my view, is also BCN. BCN, you can really see it's more reactive than most of the 8-membered rings alkyne derivatives. It's less reactive than the most reactive Barrick and DBCO. But then one has to realize that these contain large parts, hydrophobic parts, which really can affect the properties of ligands which are being attached to these moieties. The beauty of BCN, it's a relatively small compound and not too hydrophobic, although it's less reactive than Barrick and DBCO. But still, we found, we thought that that BCN is not reactive enough. It has to be more. We needed a compound which has to come closer in terms of reactivity to the copper clicked azide alkyne cycle addition. Now, and that led to the development of TMTH-Si and derivative for strain-promoted azide alkyne cycle addition reactions. And this is the reagent which we have here. And this reagent, as you can clearly see, is reactive, more reactive than most strained cycloalkyne derivative. It's actually coming very close to Barrick, but it has the advantage of being less hydrophobic. And it's actually relatively hydrophilic if you look on the scale of the lipophilicity, which is determined by the log P. Now, there is still a significant drawback, perhaps, in terms of organic chemistry. When we started thinking about TMTH-Si, we started to think about TMTH, and this reagent has been made earlier by actually pretty famous chemist in Holland, Hans Weinberg in 1966, and later on in by Krebs and Kiemling in 1970. But if you look to the synthesis of this has some challenging step. Here the acetylene condensation, here a Schwann oxidation, and here this reaction with hydrazine, and in the literature it was used tetraacetate or silver oxide. Fortunately, that could be replaced by a high valent iodine compound, but still this is a challenging synthesis. This one has been carried out. We came up with this in Crystal Therapeutics, and this has been carried out with a top synthetic custom synthesis firm, Mercachem, nowadays Semiris. And of course, they could make this particular compound, not in a very high yield, but the thing was that we could, and that this is the bottleneck, we could not reproduce in the literature of functionalizing this particular molecule, because you have to functionalize this molecule if you want to attach any ligand. So functionalization is crucial. But then the genius of this collaboration came in with Semiris and Mercachem. They could develop a derivative containing a potential handle of this TMTH. And this molecule was therefore called TMTH SI, as in sulfoxamine, because the sulfoxamine is the handle. Now, we determined the structure, of course, in collaboration with Claire Wilson of Glasgow University, and here you can clearly see the strained angle of the alkyne. And this angle wants to be released, and it really wants to be released very easily, giving rise to a very reactive derivative. But the handle was the crux for making the right derivatives. Now, of course, you first want to know how reactive is this particular compound, and we determined that in collaboration with Hans Ippel of the University of Maastricht. We looked first at the NMR, and to our pleasant surprise, this molecule was very reactive. So we could not determine the reactivity by NMR. We just let it react with benzyl azide in the strain-promoted azide alkyne cycloaddition, and we get, of course, the enantiomeric mixture, and the reaction rate could not be determined. But fortunately, we had other colleagues at Maastricht University. This is Maarten Honing, and they could determine by ion mobility mass spec the rate of consumption of TMTH-SI and the formation of this enantiomeric mixture. And if you do that very nicely and properly, you really can see that TMTH-SI is very reactive, certainly comparably reactive as Barac, and certainly more reactive than DBCO and BCN. So we were pleasantly surprised here. So, and here you also can see that the log P is very nice, so that this compound, and as a matter of fact, if you have the HCl salt, is very soluble in water. So the conclusions there is it's more reactive than BCN, so we were very happy. It has a similar reactivity as Barac, which is the most reactive compound, but Barac is not that stable, and it's far less sterically bulky, giving rise not to all kinds of bystander effect if you attach something. And it has this low log P and a better solubility. But the important aspect then next is attach something, be able to do chemistry so that you can attach a linker so that one can attach ligands to it. Now, that is shown in this slide here. We start with TMTH-SI, and a number of important linker-containing molecules can be made. Now, acylation with succinic anhydride gives this derivative, which can be converted to the succinic ester, and which is very important for amine-containing peptides, protein, antisense, SPR chips, etc. Another derivative can also react with amines, which is the carbamate here. Of course, we can convert this also to an amine, giving rise to the possibility of a ligand which can react, a derivative which can react to carboxyl-containing ligands, dyes, APIs, and whatever you have. Now, this chemistry turned out to be very convenient. Functionalizing this amine, this IMID here, turned out to be very versatile. This compound is also very interesting, and I will mention you later on, because it contains a linker which can be cleaved. So later on, you can remove it, you can remove the ligand from the cleaved molecule to have it liberated because you need it, because it's bound to an antibody and it has to be relieved for anti-cancer inhibition, whatever you need it for. So this is extremely versatile, and I want to mention a couple examples quickly. The amine can be reacted with a dye, giving rise, and the dye, if the dye is attached, you can react it with nanoparticles containing on the outside an azide, and you obtain azide nanoparticles which contain the dye for visualization. Folic acid in the treatment of cancer. If you have this folic acid derivative and you take this carbamate, you end up with this derivative here, which is powerful also for treatment or for attachment to nanoparticles and in the treatment of cancer as well. A targeting peptide, also with the succinic ester derivative, can be reacted, and we obtain nanoparticles which have this targeting peptide. So there are many examples, and I just briefly mentioned them. If you want to look at them in more detail, I would refer that to our paper, but there are many possibilities here. A very interesting possibility is the use, again, of this disulfide containing linker. Because if you have attached that, for instance, to a antisense or another RNA, you get this particular construct, which can be attached to via the TMTH-SI linker to a cell-penetrating peptide. And after cell penetration of this whole construct, you can release this oligonucleotide by treatment with, for instance, glutathione here, and the whole garbage which you just needed for making sure that this particular molecule entered the cell can be removed. So this is very attractive. Now, this is another very attractive application. I just devote one slide to it, but it says it all. If you have an antibody, and if you want to make antibody drug conjugates, you want to be sure that, of course, your click linker is going to react. If you have these relatively hydrophobic click reagents, they react not that easy. You have to use co-solvents. Perhaps they give rise to aggregation ultimately. So it's very important to have a click linker which is, to a certain extent, water soluble. Now, that's happening with our TMTH-SI linker, and you can clearly see from this hydrophobic interaction chromatography, where we have derivatized an antibody, that if you have an antibody containing these type of click handles, they're far more hydrophilic than if you have one modified with DBCO. And it's much more hydrophobic. Now, this information is very important for the preparation of antibody drug conjugates. And I'm sure in the future we will see many examples of that. Now, let me try to give you a summary of how this works a little bit. So we have TMTH-SI. Through the linker, we can introduce the cargo. Now, the cargo can be really quickly introduced with the functional groups, and there is room for extension of additional functional groups. Now you have to have the cargo attached to a carrier. The carrier can be an antibody, it can be a nanoparticle, it can be another protein. And that's happening to the click by this strain-promoted azide alkyne cycloaddition. Now, I've mentioned you the examples, and there are many more. And we get this nice cargo carrier construct, which is denoted as the conjugate. And the conjugate has favorable properties. Perhaps it's less hydrophobic because of this team THSI. It's small, so we don't have influence of this particular moiety on the biological activity of the click ligands. And that's especially interesting if the molecule is still a relatively small drugs. Again, there's room for extension to other functional groups. And what is interesting, because this reaction is happening fast here, we can prepare conjugates of labeled compounds. So having in cell studies. Now, interestingly, if we develop the chemistry, you have to know a lot about the chemistry as much as possible. And we keep on developing and gaining information about this chemistry. We know from the past that team THSI is reacting under certain conditions with alcohols. Methanol, ethanol, isopropanol, benzyl alcohol, and that's giving rise to reduction of this triple bond. Yeah, the bond is strained, so it likes to react. But if it's reacting, it's giving rise to an alkene, which is no longer susceptible to the strain-promoted cycloaddition. Now, depending on how long and how much methanol of alcohol you have, can be a complication. But so far, it's not too bad. What we found, actually, what IRIS found, because they looked at a lot of the chemistry of team THSI derivatives and team THSI itself, if you have a Boc protected compound and you try to remove the Boc group under anhydrous conditions, you get the addition of this strong acid, HCl, to the triple bond. And you obtain this vinyl chloride, which is also no longer susceptible to strain-promoted cycloaddition. From the literature, it's known that other 1,3 dipoles can react with the triple bond. Now, there are not that many 1,3 dipoles around, so actually virtually none except for the azide if you introduce it. So this is not a major problem, I think. Now, recently, Bauke Albert at University of Wageningen found that actually you can use team THSI also in inverse demand Diels-Alder reactions, meaning that you reverse the components of the Diels-Alder reaction, and this is giving rise to this Diels-Alder adduct. So that might be an interesting reaction. Now, what was found also by IRIS, that this particular compound, which is used a lot in the preparation of all kinds of derivatives containing team THSI, it's stable in DMF and acetonitrile. And I want to move to the other chemistry and stability. Under several basic conditions, piperidine, diethylamine used in the removal of MOC, conditions which are also used in the chemistry of the peptide chemistry, removal of protecting groups by potassium carbamate. Basic conditions are very good for using the team THSI. But even electrophilic reagents, coupling reagents, oxalyl chloride are very nicely in agreement with the use of team THSI. And this was work carried out at Iris Biotech. They have huge expertise in all these kind of things. And Dr. Zhang and Dr. Buchdorfer were instrumental in having the experiments being carried out. What was found actually, and was very important related to the synthesis of peptide, is that TFA during peptide cleavage and deprotection condition, TFA water TIS, was possible if you want to synthesize a peptide. Now, usually if you do solid phase peptide synthesis, if you're using the FMOC strategy, after deep protection and removal from the resin, you use these conditions, and these could be carried out and leaving the peptide intact. And this was carried out in the group of Ingrid Dijkgraaf at Maastricht University. And this is a very important finding, because other strain-promoted reagents are not stable under these conditions. And this offers the opportunity for the introduction of a TMTHSI derivative during peptide synthesis, followed by cleavage and deep protection. I cannot emphasize that enough. So that's giving rise to what I've shown on this slide. You do the synthesis, you introduce the FMOC derivative, you cleave, and you get your peptide with this TMTHSI derivative. Now, the final part of my presentation is, can we go even beyond this? Can we selectively introduce a TMTHSI derivative on the amino terminus of a native peptide containing all functionalities, including lysine, NH2s, or on the amino terminus of a protein containing many functionalities, many lysines property? Is this possible? Because that would give us a huge possibility for the selective introduction of TMTHSI for all kinds of purposes. Now, I would not show this slide if it was not possible, and indeed it's possible. So if you take this particular peptide, and you can actually achieve this. Now, how did we do this? We were inspired by the paper of McDonald's in Nature, and they found that using this reagent, you really can selectively modify the N-terminus of a peptide or protein. So we took the opportunity of taking this particular reagent, introducing TMTHSI, making this particular reagent. This was carried out, of course, in collaboration with Cymerus. And we took this particular reagent, we took octreotide, which is containing also lysine, and we just got one product. And actually, I have to be a little bit more honest. It's one product, but it's a diastereomeric mixture. But it's one product that is reacting only with the amino terminus of this cyclic peptide, giving rise to the formation of this diastereomeric mixture, which can be easily seen in the HPLC trace. So this is really great news. And if you go beyond this and take a peptide which contains several lysines here and do the same reaction, you end up finding just one diastereomeric mixture reacting of the reaction of this TMTHSI derivative selectively with the amino terminus. So this is a great finding. Having many lysines there doesn't make a difference. You get your product at the N-terminus, which is clearly here. So then the final challenge, of course, is, can we change this? Can we achieve the same reaction using a native protein? Now, for that, we thought we needed a somewhat different derivative, just to be sure. Matt Timmers came up with this idea. Now let's put something in between the TMTH click handle and the one which is reacting with the N-terminus, adding to the hydrophilicity of the thing and making sure that we don't get any problems with reactivity because molecules are moieties are too close. So we modified angioPep2, which is already a bigger peptide, with this particular reagent, which was, I think, this case made by TBD. I mentioned them later on. And again, we get a molecule which is not reacting with other functional groups and reacting selectively at the N-terminus, giving rise to this diastereomeric mixture. The problem is a little bit, but that's a workup problem. Perhaps if you do an HPLC workup and this derivative is too close in terms of retention time to the product, you have to get rid of this particular access, because else it will react later on, also with a click reaction, if you want to attach this particular product to another azide containing molecule. Now for that we found a good solution using hydroxylamine containing beads. And you can remove this use that for removal of the excess of this TMTHSI glycol 2-PCA hydrogen. Now, very recent results obtained in a group of Ingrid Dijkgraaf by Wouter Peters showed that we could take Afazin-3, which is a thick protein, and of course you want to use that for vaccination purposes. It's a big molecule. If you take this with TMTHSI glycol 2-PCA, you react it, you get one derivative, which is great, the N-amino terminus. You want to crank up the antigenic or immunogenic properties a little bit more, and you use this bacterial designer protein. And this bacterial designer protein can be clicked to this particular moiety here, and we get this construct here, and this can be used for vaccination strategies. So that's a great result. And so I think I'm sure we get more of these examples in the near future. Now, this concludes more or less the scientific part of it, but I want to end up with some conclusions here, which are practical and very important. And the reagents are now available from IRIS Biotech. Very important that, but what is also important, that new derivatives are synthetically easily accessible, and you can think about that yourself, but also discussion with IRIS, because you have heard that they have great labs, and if there are new derivatives necessary, I think I would really recommend to start in discussing that. Now, for research purposes, there's no problem with that, to buy this stuff and use it. Now, Lonza found also that Clicker was really very nicely for using in bioconjugate applications, so they will look at that as well. Synaffix, very interesting. They found that Clicker is also very interesting, and Synaffix has been taken over or has been acquired by Lonza. So that's an interesting construction for the future and future development. I think that shows that there is tremendous possibilities here. Now, what is also very important, that one can produce Clicker on a large scale. And although I was personally, but I'm an organic chemist, I was very hesitant in saying, oh, is this going to work at all? Now, I can tell you these compounds can be made in more than 100 grams quantities, several 100 grams quantities. And the stability of these building blocks, TMTHSI, but also the subsequent building blocks, as I told you, are very good under diverse conditions. It means that manufacturing and upscaling is possible, and that has been confirmed by the external CDMO. But if you want to use for more than research purposes, then I think you have to start talking to the people who really know how this Clicker should be handled, because there is a pretty strong patent position. And a number of derivatives can be patented, and a number of applications are really very interesting. Now, if you want to discuss that, you have to discuss that with people involved in that. That's Christiane Rijke and Werner Cottrails, and they know everything about this. But I certainly would encourage you to use Clicker and derivatives in your research. And who knows, you can actually start developing a very interesting application, which we can develop then together. Now, I'm now almost at the end of my talk, but this is very important, and these are the acknowledgements. First of all, I want to mention Christiane Rijke. We know each other for a long time, almost 20 years, she said. And she is the founder of Crystal Therapeutics and CSO and CEO. We have collaborated for many years, and thanks to her high interest, huge interest, I would say, and fantastic energy, we are here where we are. That's also due to Jimmy Weterings, who was the head of chemistry at Crystal Therapeutics until the end of 2019. He was really a very bright organic chemist, and he no hesitation what kind of difficult chemistry, and he started developing TMTHSI together with Merck, leading to the great results we see here. Now, Mats Timmers, he is a highly promising member of the new generation of scientists. And I'm sure science and chemistry will flourish in his hands. And that will also be the case with Marco, perhaps in a little bit farther future. But these are the people really make the future and perhaps look at the nice applications here. Now, what you see on this slide is the necessity. We always realize that more or less in the academics, but in companies you realize that more and more that you need very good collaboration. I've already mentioned you the collaboration with Maastricht University, Ingrid and her colleagues, and Hans Ippel, NMR, Martin Honing, Mass Spec. But what's very important is also the chemistry with companies who really can do top chemistry, and that's Samiris and Merck. The people here involved, Tommy Meulemans and Harold Veldhuis, were instrumental in developing TMTHSI, which was taken later by Andy Kipper and his colleagues in the development, in the large-scale development, and they did an amazing job. And of course, Lonza, Iris, and Synaffix realized the potential of the TMTHSI derivatives. And they can take it further to very nice development. But I wouldn't be here at this stage if my colleagues at Utah University and at the University of Glasgow had not done a lot at the very start of the copper click chemistry and also the sulfur click, and realize the huge potential of click chemistry for chemical biology and medicinal chemistry purposes. Now, I think I've already taken too much time of your time, but I certainly want to thank you for your kind attention. Thank you very much.
Yeah, thank you, Rob, for sharing those really interesting results with us. Yeah, dear audience, please excuse us for the little technical issues we have in the beginning. So you see, this is really a live webinar, not a recording. We have collected quite some questions during your presentation. So, Rob, in the very beginning, one was, so you recommended to us this very fast and superior method. Would you still recommend to use the copper catalyzed click reaction in certain cases? And which cases are those where you would still go, say, with the classical method?
Yeah, thank you for this question, Raymond. I certainly would recommend still copper click, because and the examples I showed you, also for synthetic vaccines and protein mimics, they really can, you can use copper click there very easily. And why is it nice? Because the azide is easily introduced, the alkyne is easily introduced, but with these things you really have good purification methods. And we determined actually very nicely, or we were pretty sure, if you don't have a chelator like the octreotide example, click chemistry can be used for these constructs. So I certainly would not hesitate to use them for instance, a number of synthetic vaccine purposes or for some kind of protein mimics. But where it becomes very crucial in pharma and so on, ADCs, then you certainly have to move beyond that. So there's still a number of cases where you can use it. I'm confident about that.
Okay, so then one question to the structure of the TMT HSI. So obviously you were starting with, say, the historical molecule of TMTH.
Yeah.
And so have you ever tried other substituents than the 4-methyl groups, for example, hydroxyethyl or so, to even further increase the water solubility?
In the patent applications, there are some other derivatives, but what is important to realize that you have to have functionalities which cannot give rise to the decomposition of the alkyne. So,
Yeah.
of course, it's very important to have the methyl substituents because they cannot give rise to the formation. If you would not have the methyl substituents, you would get an allene-like structure, or you would get complete decomposition. So the methyl substituents are important. Hydroxymethyl, which could give rise to an increased water solubility, could be interesting, but we know that alcohols can be detrimental for the alkyne. So you would have one molecule which is water soluble and reacting with another one and giving rise to a reduced form of the alkyne. The only possibility would be ethers, but then still we would like to keep the molecule as small as possible. So this is perhaps the smallest molecule which has still the most interesting properties. But there are some possibilities, still some possibilities there. Yeah.
I see. So something a bit similar. What was that question? Yeah, so that was one question that came up before you switched to the stability slides. That was, are there reaction and surrounding conditions that Clicker is not compatible with compared to other strain cycloalkynes? So you showed, for example, that things with methanol.
Yeah, if you leave it.
And in how far is there? Most of the say side reactions are with the alkyne component. So I guess most of those side reactions would also happen also with other strain cycloalkynes. But
Yeah.
Which are the problematic ones, particular on the TMT HSI?
The most problematic we thought was the reaction with alcohols.
Mm-hmm.
And but then if you can avoid methanol or isopropanol, isopropanol, benzyl alcohol. Now, benzyl alcohol you will not use that much. Isopropanol, I can imagine. Methanol or ethanol, it's going to be a little bit more, but it's those are the most problematic. So if you would use it and leave it in methanol or ethanol, then the compound is gone ultimately. But then you would not use those reagents usually in that much in a bio environment.
I see. Yeah.
So we found that, yeah, of course you can decompose these things and you can reduce them, but the problem is not there if you don't use those reagents that much. And we found actually if you have, I think it has been found perhaps by you guys or perhaps by Synaffix, if you have eluents, methanol dichloramethane eluent for purification, there was not that much of a reduction there. So pure methanol, pure ethanol, pure isopropanol, benzyl alcohol, I think that will give rise to problem. And it's always the strained triple bond. And yeah, and of course, TMT-HSI, like BCN or TMT-HSI is, and also like Barack, are the most reactive components, so they will react on that moiety. Barak is even more sensitive, and PCN will also react on the acidic conditions on the cyclopropane, which is there.
Yeah.
What we do see, what we do see with the sulfoxamine doesn't react. There's no stability issue there. That's pretty stable. That's really stable. So it's the triple bonds.
Yeah. Okay. So, and another thing, a question from somebody from the audience. How about the thiol-ine reactions? So the thiol reaction with the ring-strained alkyne. Have these been investigated for the TMT-HSI, and could such reactions be aimed for in place of using an acide?
Yeah, that's a very interesting question. I think perhaps as we speak, because we're still looking a little bit at the stability of the TMT-HSI, whether it's reacting in a kind of so that you get a thiol-ine click reaction, so that could perhaps be the case. But at this point, honestly, we don't have definitive data around how reactive it is with a thiol. And meaning a thiol is mercaptoethanol or glutathione. But that's under present investigation, and we really should know this. But perhaps we can use it to our advantage as well. And
I think so. Yeah.
Yeah, absolutely. So this needs some more work, and I would encourage people there, and that's to share that. And the more you know about this particular molecule, the more you can do with it, and knowing the limitations. I think what could be the biggest disaster is that people try to do something with TMT-HSI and they say, oh, it's not working, without telling and sharing this information. And negative results are just as important. And if we know these things, then one can start using this molecule as in the most optimal form.
Yeah. So this is really an information that I would also like to share with the audience. Whenever you encounter problems or you see any side reactions, please report them to us. This is really helpful and fruitful information for all the others that may use it after you. So please share your experience with us, with Rob. I really encourage you to do so. Another question. So you did not really speak too much about tetrazine ligations, which is also a very fast reaction. Why are you not so much interested in that kind of reaction? Or
I think it's a very interesting reaction, but I think we are so much, perhaps we are a little bit too much focused. But I think the beauty, and that's why I went so much about copper click. The beauty of this reaction and also of sulfur click is that you have relatively simple but also small components, and still with the tetrazine reaction, it's going to be bigger. The tetrazine part is going to be bigger. The cyclooctane, that's okay, but you need a trans one, and it has some problems there as well, giving rise to the formation of the cis. So, although I think it's a very important development and it's very quick for some for imaging purposes, and I think it's a still very good reaction. What we like this particular the reaction so much because they are simple and small. Perhaps we should say that, simple and small.
Okay. So one question from Thomas was, I think you already answered that by the end of your talk. Can bulk quantities of Clicker be provided for commercial applications? So what is currently the quantity range you could provide in case of demand?
I think that's going to be, and if people, if we really want that, but in these non-research quantities, yeah, they really should speak to Christiane and the Cortrails. But in principle, the quantities for research purposes can be certainly grams easily.
Yeah.
And
so as you reported,
yeah,
obviously, even currently, several hundred grams are not a problem.
But then, you know, as soon as people starting using 100 grams or tens of grams, you're entering. I think I would say you're entering the non-research aspects.
I would think so too.
Yeah,
right.
and then you should talk to the people who really know more about this than I do.
So one question from Mark Brunstrup, which goes a bit in the same direction of later commercial products, is to clarify, assuming he prepares any new conjugate with a clicker moiety, with something of his portfolio and wants to patent then the active compounds. Would he then need a license from Crystal Therapeutics, no matter what the carrier of the effectors are? I would assume so, yes. That would definitely be a topic to get into contact with the clicker patent owners.
I certainly would say you have to contact them people, but I think it should not be, and I think it's not. I think everybody's interested in new developments and interesting developments. So, although of course it's important to contact each other and to discuss this, I think it's not an obstacle. It's not a obstacle for not collaborating. It's not an obstacle for not entering a joint venture and so on. I think nobody is seeing right away in each other's eye dollar signs or euro signs. I think this is not the way it should be done, and I think that's also not the case if I know the people of Crystal Therapeutics. So I think there will be issues around patenting, and there is of course a good protection of TBTHSI derivatives. But it should not be an obstacle for entering new and exciting areas.
So exactly, that's it. So because a similar question came up then, in extension to which click handles are indeed free to operate for product development. This is really, I can encourage you.
Yeah.
Those products that you can acquire, for example, through Iris Biotech, these are original products and you have freedom to operate, to try them out in your research and development projects. So you can attach other handles. That is your research project. As long as you're doing research, you have freedom to operate.
Yeah.
And as soon as it's going into further project stages, then please approach us and Crystal Therapeutics. Then, of course, we should speak with each other. And as you said, this will not be the big obstacle. Everybody involved in this topic is keen on going further and having new applications for that. So let me encourage you really to try it out. I think you won't regret it.
Yeah, I fully agree. Talk to Christiane and Werner about this. This is, should be not an obstacle.
Yes. So currently we do not see any further questions within the chat. Again, if you have any further questions coming up, do not hesitate to contact us also afterwards, and we will forward those questions. With this, I would like to close our online workshop. Iris Biotech has, as already said, some interesting clicker molecules of crystal therapeutics in its catalog portfolio. You can find them on our web shop under Products, Click Chemistry, Products with Clicker, and of course, many other variations are accessible through an individual custom synthesis. As a follow-up, we will provide the recordings of this workshop online. Thanks again for joining us. Thanks to all our speakers, and also a big thank you to our QA manager, Klaus Helm, for taking care of the technical support. We hope you could collect some helpful ideas and information from this workshop, and you make some interesting experiences with this new elegant technology. We are looking forward to meeting you in the next workshop in September, which will be announced on time on our homepage and via social media. So enjoy a beautiful summer, stay healthy, and hopefully see you soon. Goodbye.
Thank you. Bye.